Hello, my name is Emily Kroll, and this is a training video to give you background information on X-ray diffraction. So what do X-ray diffraction machines do? These machines are incredibly powerful and can be employed to run many different types of analysis. Some of the most common uses for XRD machines include analyzing the crystal structure and even performing quantitative analysis of phase composition. It is used for finding the crystallite size and microstrain, but it can also look at the strain on a macro scale, known as residual strain. XRD can identify defects in samples. It's used to identify and characterize polymorphs. Texture orientation can be found, and unit cell lattice parameters and Bravas lattice symmetry can also be analyzed. Not only can it be employed to analyze crystalline materials, but it's also frequently used for its ability to identify amorphous materials. X-ray diffraction is extensively used in material characterization. In material characterization, it's necessary to identify both the elements present as well as the structure in order to fully define the material. Unlike other characterization methods, XRD can provide information on the elements as well as their structure, which is defined by the atomic arrangement. A material composed of only one element is called an allotrophy, and this can be a polymorph. A polymorph is a material with the same composition but different structure. The best example I can come up with is carbon. Carbon can either form graphite or diamond or even an amorphous structure depending on its crystalline form. So in the case of carbon, it's extremely important to not only identify the element carbon is present, but also the structure that it takes to understand what material you're working with. So how does XRD actually do this? The best place to start is Bragg's law. Bragg's law is used in defining a material using X-rays, which have very short wavelengths on the scale of an angstrom, and these are aimed at the sample. When the X-rays hit the atoms in the sample, the path of the X-rays is altered. In 1912, W.L. Bragg discovered the relationship between the wavelength of an X-ray and the angle of diffraction and the distance between the internal planes of a crystal. And this is Bragg's law. The wavelength is denoted with lambda and is proportional by an integer n to 2 times the spacing between the planes, d, which is multiplied by the sine of the diffraction angle, theta. Diffracted X-rays interact with each other and can either have a constructive or destructive interference. Destructive interference occurs when the waves are out of phase, meaning that the peak of one wave coincides with the peak of an opposite amplitude in the other wave. Essentially, the two waves cancel each other out. On the other hand, constructive interference occurs when the waves are in phase, meaning that the positive peaks of the two waves are aligned and the waves are amplified. Whether or not the X-rays will be constructive during XRD is determined by the material properties of the sample and the angle at which X-rays are applied and detected. Now that we know how Bragg's law relates to the diffraction angle and the lattice spacing, we can take a look at how XRD machines use this law. First, we need to identify the basic setup of the machine. It includes 3 main parts: the X-ray tube, the sample mount, and the detector. In order to find the lattice spacing using Bragg's law, a rotation must take place so that the X-rays can be detected at various diffraction angles. In any XRD machine, there will be two of the 3 main parts that will rotate. For many machines, the source is fixed with the sample and detector rotating, but for others, the XRD machine has a fixed sample mount, while the X-ray tube and the detector rotate about it. An obvious advantage to having a fixed sample mount is that the samples are liable to slip off the stage if it's rotating and the angle becomes too great. However, the rotation of the source and the detector is very demanding on the machine, so that is why some of the machines have a rotating sample plate. The angle that forms between the source of the X-rays and the sample on the XRD machine is omega, and then the angle between the detector and the incident beam from the X-ray source is consistently at 2 theta, meaning that it's always double the omega angle. So that's the basic setup of the machine. Taking a little bit of a closer look, here are some more parts of the machine that you'll need to know. One is the X-ray tube, or the source. Just to the right of that are the solar slits and divergent slits, which make up the primary optics. In the very center is the sample holder and sample stage. Then to the right of that, highlighted in blue at the top, is all of the secondary optics. And then lastly, to the farthest left is the detector. An X-ray tube is used for the source of the XRD. This is either a ceramic or glass container that has a tungsten filament that acts as a cathode. This cathode filament emits electrons, which then pass through a series of nuclear cores that accelerate them. This causes a white radiation effect. The accelerated electrons then travel to a target anode material where the electrons bombard the element's atomic structure, causing secondary electrons to be kicked out of the electron shells. The hole in the electron shell caused by the secondary electrons being expelled leaves it in an unstable state. That is when electrons from higher energies will drop down to fill the space. However, in order for these electrons to go from a higher energy level to a lower one, some energy must be released. This energy released is in the form of X-rays. A characteristic amount of radiation is emitted from the target material depending on the energy level of the atom as well as what target material is used. Typically, the target material is a copper, and the characteristic radiation is classified as either K alpha 1 or 2 or K beta. In order for the X-rays produced in the source to be effective as possible, there are primary and secondary optics that condition these X-rays. The primary optics conditions the X-ray beams prior to hitting the sample, and the secondary optics receive the X-rays that are diffracted by the sample before they go to the detector. The primary optics can be broken down into three main parts. First is the solar slits. These keep the beam on the correct plane and allows for data with narrower peaks and less asymmetry to be collected. While the solar slit keeps the beam in the correct direction, the divergent slit controls how wide the beam is. Lastly, there are monochromators in the primary optics that act to filter out unwanted radiation in the X-ray beam. This only allows K alpha 1 and K alpha 2 radiation to pass, and it filters out any of the white radiation or the K beta radiation. The monochromators, much like the divergent slit, greatly increase the resolution of the data that is collected. Let's take a closer look at the solar slits. These slits are metal foils that are stacked in parallel with constant spacing. Like we mentioned earlier, the job of the slit is to reduce the angular divergence of the X-ray beam and to keep it on the correct path. By doing this, the peak asymmetry of the signal will be greatly reduced, so you'll get better data. The divergent slit is used to block X-rays that have too great of a divergence. By reducing the spread of the beam, which is known as the height divergence, the resolution of the output is significantly increased. The divergent slit comes in a variety of sizes, which affect the peak intensity and the shape of the output. For example, a narrow divergent slit will reduce the intensity of the beam, the length of the X-ray beam, produce sharper peaks, and allow for greater resolution than a wider divergent slit would. Let's take a look at the secondary optics. The secondary optics are on the receiving end of the X-rays that were diffracted by the sample, and can be broken down into four main parts. The selection slit, which is known as an anti-scatter slit, reduces the diffusion or scattering of the X-rays that occurs due to amorphous or air scattering. The height limiting slit, which is again a type of solar slit, reduces the axial divergence and limits the beam height. The receiving slit is next. It is the height divergence limiting slit that removes diffuse scattered X-rays that occurs from previous elements in the secondary optics. And lastly, the beam passes through another monochromator. The monochromator acts just as it did in the primary optics. It absorbs K beta radiation and white radiation, while allowing only K alpha 1 and K alpha 2 allowed through. During the actual detection, the X-rays are absorbed by a compound that then emits visible light. This process of converting X-rays to visible light is called scintillation. The scintillation compound can be organic or inorganic crystal, or an organic compound dissolved in a solvent of sodium iodide activated with thallium. A photomultiplier is used to detect the visible light from the scintillations. The photomultiplier detects photons and then produces a proportional electrical voltage, which is the actual source used by the computer to create your output. So the results for the XRD can be seen on a graph that plots intensity versus 2 theta. It is important to keep in mind that the peak position as 2 theta depends on the instrument parameters such as wavelength. Therefore, Bragg's law is used to relate this position to a material peak position that is instrument independent. The spacing of the peaks can be used to define the crystal cell unit because the distance between diffracting planes of an atom is what determines this peak position. The peak intensity is based on counts, which is the number of X-rays detected for a given peak position. The intensity is determined by the atoms that are present and the diffracting angles. Therefore, intensity gives insight on the elements that are present in your sample. XRD also takes into account the width and the shape of the diffraction peaks by using the Schrödinger equation. This relates the peak width and the crystallite size. Here at CMSC, we use a program called JADE that analyzes the XRD peaks and profiles using these characteristics. It's an extremely powerful program, and I suggest you learn into using it more. If only one single crystal is being analyzed, the standard Bragg-Brentano setup we discussed earlier, which is the standard setup for an XRD machine, would only show one set of peaks. You can see that the peaks from this crystal are only observed when the planes are aligned such they bisect the incident and diffracted beams as they do at 100 and 200. But if the planes are not properly aligned, like they aren't at 110 peak, then there will be no diffraction at all and you can't see a peak there. On the other hand, if there are multiple crystals present, let's say in a powder form, then this problem can be circumnavigated. This is because the packed powder forms all the crystallites with different plane arrangements that are randomly oriented. Therefore, there will be a number of crystallites that are properly aligned to diffract in all orientations at some point in the powder. For powder diffraction, the size of the particles should be between 10 and 50 microns. The powder is packed into a sample holder using a spatula to ensure that the divot in a glass slide is filled and the surface is as smooth as possible. If you're doing more of a bulk sample, there are holders for that as well. You can see some examples of them below. There are many parameters that need to be set to determine how well your data collection will go. These parameters have to do with the characteristics of the equipment, such as the slit width, and the settings of the power source, and how the rotation is controlled, and the data is collected. It is best to read articles related to your project for a guideline when deciding how to control these parameters for your sample. There are a few very common sources of error when collecting data from XRD, and many of them can be easily avoided. The most common of all is sample displacement. This means that the sample is not in the correct place, and it's not in the focus of the X-ray tube or the detector. So just put your sample where it's supposed to be. Easy fix. Axial divergence can be minimized with the primary and secondary optics, but if the X-ray is in place with the sample, it can cause divergence. A flat specimen error and poor counting statistics can both be avoided with better sample preparation. A powder sample should be thick enough to prevent the X-rays from passing all the way through it. Lastly, sample transparency can cause a shift in the peaks due to the diffraction beam being partially displaced, and this can lead to inaccurate peak profiles. Like any machine, there are limitations. To get the best results, a homogeneous sample with a single phase can be analyzed. For composites or mixed materials, the limit of detection is about 2%. So if there are any elements present that make up less than 2% of the samples, they cannot be detected. Once a profile peak is collected, there must also be a reference file in order to identify what that material is based on that profile. Fortunately, there are such reference libraries at our center. Other limitations for this process is that there's a sizable amount of the material needed in order to run the test. So if you don't have very much of your sample, it will be a challenge or impossible to run XRD. Lastly, if the sample is being run at high angles, there may be peak overlay, which causes inaccurate peak profiles. Thank you so much for listening to this video. I hope you found it helpful.